Okay, let's talk about section 6.3. Exponential functions. Exponential function, we have the power. We know that if you have a number, for example, a, we take n's power. It just means the product of a with a with a with a n times. And we also know if we have the power 1 over n, it by definition means the nth root. And also we define the negative power as a reciprocal of a to n, the reciprocal of a to n, which is 1 over a to n. Put all these things together, we can define the following thing: a to n over m for arbitrary rational number n over m. It means you take nth power first, or mth root, or you take mth root first, nth power. Okay, so this is the power function. So basically, we know the meaning of a to r for any rational number. R. We have the definition. A to r. But we do not have the definition of a to r when r is irrational. So basically, what is the meaning of a to pi? We have no idea. What is a to pi? So if we want to clearly give the definition of a to pi, it requires the calculus. But here we try to understand it this way. Pi is approximately 3. So it's approximately 3.1415926. So then we believe that a to pi should be approximately as a to 3.1415926. Okay? And this is a rational number. For this rational number, we know what is the meaning. Even though it is written as a decimal number, but it's actually a rational number. We have the definition. And it's approximation. If you want a better approximation, you just get a better approximation of a pi. So you get a long decimal number, you get a better understanding of a to pi. So this is a way for us to understand the exponential, the power function when the power is irrational. But that's just I mean, this is a correct way, but still so far we don't have the correct language to describe it. So we will just believe we already define the power function when you have an irrational power. And the value, of course, should be approximated by the value of a to the approximation of this irrational number. And one more thing, even with a rational number, for example, even with 2 to 1/2, it is a square root of 2. It's irrational. So in order to get this number, we use calculator, and the calculator will just give us an approximation. So when we do this type of approximation, it also makes sense. We don't need the precise value, we just need the approximation. So it does not lose a lot of information, right? we can only get an approximation of square root of 2. Okay, so if we don't get a precise value, we just use approximation. This is a good enough way. So now we believe we understand all the power functions. What is a power function? So we understand when you have a, we can put whatever power here. And this is called an exponential function. Exponential function, the base is a fixed number. Okay, so this is a fixed number. Okay, it's called the base, and the x is the exponent. And for most of the value, this is an irrational number. We can only get approximation. Okay, so you in the textbook, they give you a list of the practice. They ask you to use calculator to compute what is a 2 to 1.4. What is 2 to 1.4? In symbol, it's the following. 1.4 is what? It's a 5. 7 over 5. It's 2 to 7. 7 over 5 is 1.4. So it's 2 to 7 over 5. 7 over 5 is you take 5th power of 2 and then you take 7th power, right? The numerator is a power, denominator is a root. So that's a irrational value. So you can use a calculator to get approximation, right? And you can get the estimation of this value and the estimation this value, and eventually if you put something like this, you will get estimation based on the calculator, just based on the calculator. We don't do the computation by hand for those type of numbers. They are all irrationals. And we choose this sequence because of 1.4, 1.41, 1.414, they are the approximation of square root of 2. Square root of 2 is approximately 1.41421 stuff. So you can do this approximation. You will see from the calculator they becomes closer and closer. Okay, yeah. So this is an idea. We use the approximation of a rational function to approximate the power a to the irrational number. Okay, so that's a explanation about the exponential function with a irrational power. For rational power or irrational power, we always have this law of exponents. Laws of exponents. So for laws of exponents, you have the following thing. A to s times a to t is a to s plus t. The product with the same base, the product of two exponential expressions with the same base is equal to a to the s plus t. And the product, the quotient corresponds to the difference of the exponents. And if you have power s and then power t, it is equal to power s times t. You have a times b to power s, it is a to s times b to s. And of course, 1 to whatever power is equal to 1. Here, this s could be irrational. Even for irrational number, 1 to s is always equal to 1. And if you have a negative power, it is the reciprocal. it's the reciprocal. And the final thing, for whatever number the value to 0th power, a to 0th power is 1. And be careful, when we talk about exponential functions, we require the base always positive. We require the base always positive. So let me explain why we have such restriction. Of course, when we get concrete number, for example, negative 2 cubed, it is equal to negative 8. This is good. Or negative 2 to 1/3 is negative, the cube root of negative 2. It's also okay. But we do not have this one. At negative 2 to x is never defined because this x can be 1/2. For example, when x is 1/2, you will have a negative 2 to 1/2, which is a square root of a negative 1/2. This one is undefined. We are talking about the real case. Don't put this together with a complex number. This is a real case. For the real stuff, this one is undefined. Okay? So for the negative number, you have to remove all the, like 1/2, 1/4, 1/6, or 3/2, or 5/6. You have to remove all those numbers with an even denominator. That's very, it's annoying. So we don't want that happen. So that's why we do not want to remove x equal to the 1/2, 1/4, 3/4, 5/6, because for all these rational numbers, you will take the even root of negative 2. They are undefined. We don't want to remove all those values. There's infinitely many. So we exclude negative 2 as a base. We exclude the negative 2 as a base. Okay? So the negative 2, all the negative number cannot be the base. Whenever you talk about exponential function, the base is always positive. Okay, so all these expressions, they have the requirement A, B are positive. Okay, and now let's see. Definition. An exponential function is a function of the form fx equal to c times a to x, some coefficient where a is a positive number, a is not equal to 1. Okay, so when we talk about the exponential function, we also want to remove 1. 1 is positive, but still we want to remove. Why? Because when you have base 1, you have a constant function. Constant function is not interesting at all. So we don't want to study that trivial case. And the coefficient, of course, the coefficient is not equal to 0. If coefficient is 0, to make this whole thing 0. Okay? And we talk about a real case, so coefficient is a real number. Okay, now let's make it clear. Only when we discuss the solutions of polynomials, especially with the fundamental theorem of algebra, we are interested in the complex numbers. Otherwise, in the pre-calculus and the calculus, without additional requirement, we only just discuss the real numbers. Even though we know there are complex numbers, but without additional requirement, all the x's, y, a, b, c, they are real numbers. But only for the fundamental theorem of algebra, we mention the complex numbers. And for the quadratic functions, we mention the complex numbers. And in that case, we also always emphasize in the complex number system, what is the solution. In the real number system, if the discriminant is less than 0, there's no solution. But in the complex number system, when the discriminant is negative, we still have two complex solutions. Okay? So that's the clear. So this is always a real number. And the domain of f, so you can take whatever power, is the set of all real numbers. The base A is called the growth factor. The growth factor. And let's check this f of 0. F of 0 is c times a to 0. A to 0, check here, a to 0 is 1. So it's equal to c. So c is a value at 0. 0 normally we consider it as a starting point, initial point. So c is called the initial value. Just because it is a value when x is equal to 0. It's called the initial value. Okay? So this is our exponential function. Exponential function is c times a to x. A positive, not equal to 1. C is not equal to 0. It is arbitrary real number. It can be positive or negative. And the base is called the growth factor, and the c is called the initial value. And the domain is a set of all real numbers. You can put any x here as a power, as an exponent. Okay. For the exponential function, there is an interesting property. The property is the following. Let's see, fx, this is fx. Let's check what is fx plus 1. If we give it a step, you start from x, you get a 1 step plus 1. Then it is equal to c times a to x plus 1. C times a to x plus 1 by this laws of exponent. A to s plus t is a to s times a to t. So here is a c times a to x times a to 1. A to 1 is x, a to 1 is a. Okay, so this is f of f of x plus 1. Right? And this expression, c times a to x, or c times a to x, this is fx. So you see here, you add 1 for x, you actually multiply the function by a. Or you can divide it by this fx, you will get fx plus 1 over fx. It is equal to a. This is a property of the exponential function. It's a property of an exponential function. There. For an exponential function, fx equal to c times a to x, fx plus 1 over fx is equal to a, or you write it the other way. Fx plus 1 is fx times a. Okay, so this is a very important property. Technically, it characterize the exponential function. Only exponential function has this property. Okay? Now let's try to see the graph of an exponential function. To graph it, technically you just get values, get input, get output, get input, get output. It's a very tedious job. But check our definition. This is exponential function. We have a positive, a not equal to 1. 0, positive, so we only discuss this part. A is not equal to 1. This part is not included. So this condition naturally gives us two choices. One choice, a is between 0 and 1. The other choice, a is greater than 1. Right? So when we define an exponential function, it's a c times a to x. C is a constant, it does not change. A is also a constant, but this a is a base. The base has a condition. It has to be positive, but it cannot be 1. So has to be positive, it's the right part. Not equal to 1, so you have a whole, then you have two pieces. Now let's discuss the behavior, the different behavior of those on those two different branches. For example, when a is greater than 1, let's just select a is equal to 2. Choose a is equal to 2. When a is equal to 2, of course, to simplify it, let's choose c equal to 1. We don't want the a fraction of c. Okay, let's say this is fx, now this becomes 2 to x. When x is 0, 2 to 0 is 1. Okay, x is 0, 2 to 0 is 1, this is a 1. X is a 1, 2 to 1 is 2. This is 2. X is 2, 2 squared is 4. 3, 4. X is 3, 2 cubed is 8. It grows very fast. 4, 5, 6, 7, 8. X is 4. 2 to 4 is 16. Well, we possibly don't have that point. 9, 10, 11, 12, 13, 14, 15, 16. It's possibly here. So it's already like this. Okay, let's talk about the other part. When x is negative 1, 2 to negative 1 is 1 half. Negative 1 half. When x is negative 2, 2 to negative 2 is 1 over 4. Negative 2, 1 over 4. And when x is negative 3, 2 to negative 3, 1 over 8, it is even smaller. So it rapidly goes to 0. So this is a graph of the exponential function 2 to x. Okay? So it's a rough computation, right? So that's exponential. The exponential function when the base is 2, and you can check that when the base is 3, the graph is more or less the same thing. At 0 it's a 1, at 1 it's a 3, at 2 it's a 9. It just goes faster, right? It just goes faster. So but the big shape will be the same. So let's summarize what we have about the property. So properties of the exponential function fx equal to a to x where a is greater than 1. Okay, so first, this list is on page 426. First, the domain is negative infinity to positive infinity. You can define for whatever x, either negative, positive, or 0. And the range is from 0 to infinity, because the whole graph is above x-axis, so it's from 0 to infinity. It can be as small as possible, but it cannot touch 0, and it will go to as high as possible without limit. Okay, and 2, there is no x-intercept. The graph of a to x does not intersect x-axis. The y-intercept is 1. It always crosses y-axis at 1. X equal to 0, 2 to 0 is 1. X equal to 0, a to 0 is equal to 1. So the y-intercept is definitely 1. And 3, the x-axis is the horizontal asymptote. Because when x approaches negative infinity, it will be extremely close to x-axis, but never touch x-axis or cross it. No, it's just the x-intercept. As x approaches negative infinity, approaches positive infinity, it will be as high as possible. There's no limit. Okay. Okay, and 4. You see here this function a to x is always increasing. It's an increasing function over the whole domain. Because it is increasing, so it is 1 to 1. Remember that we mentioned that increasing function is 1 to 1, decreasing function is also 1 to 1. Okay. And 5. For this function, let's see, this point is always on the graph. The point, when x is 0, y is equal to 1. And when x is 1, x is 1 is a, y is a. X is negative 1, y is 1 over a. Okay, so we just mentioned those 3 special points on the graph. Those 3 points are always on the graph. And from the sketch, or not sketch, from the calculator graphing, we can see that the graph of fx equal to a to x is smooth and continue. There's no corner or gaps. No corner, no gaps. Gap means it's discontinuous. No gap means it's continuous, right? No corner, no gaps. So this list is on page 426. You can check this page. Okay, so this is a collection of the properties for the exponential function when the base is greater than 1. What happens if you have a smaller base? You see here, this time we choose a from this infinite intervals. Now let's select a between 0 and 1. So we can choose, for example, a as 1/2. A as 1/2, we do the similar sample. So -1, -2, -3, -4, -5. when x is 0, when x is 0, it doesn't matter what a you have, it's always 0. So 1/2 to 0 is 1. This is a 1. When x is equal to -1, let's check this part. When x is -1, it's 1/2 to -1. Negative power means you're going to flip it down to the denominator. 1 over 1/2 is 2. So at -1 is equal to 2. When x is -2, 1/2 to -2 is 1 over 1/2 squared. Whenever you see negative sign, you just flip it to the denominator. 1/2 squared is 1 over 4. 1 over 1 over 4 is 4. 3, 4. And if you have a -3, 1/2 to -3 is 1 over 1/2 cubed is 8. 5, 6, 7, 8. And for x equal to -4, 1/2 to -4 is 16. You just put it on the denominator, you get 1 over 16, and flip it back, you will get 16. 9, 10, 11, 12, 13, 14, 15, 16. Okay, so you connect them. This is the negative part. For the positive part, when x is 1, 1/2 to 1 is 1/2. X is equal to 2, 1/2 squared is 1 over 4. And 1 over 4, 1 over 8, it will be very close to x-axis. Don't cross or touch it. Okay? If I can sketch it better, I will not cross or touch x-axis. Okay? So if you check that, actually those two graphs are symmetric. When you have 2 to x, you flip it to the left, you will get the graph of 1/2 to x. You flipped it to the right. Because this one, 1/2 is 2 to -1. 1/2 is 2 to -1. So 1/2 to x is 2 to -1, and x, remember the property, it is 2 to -x. What is the property? Property is here. Sorry, this is a property. To s and then to t is a to s times t. So here, to -1 and 2x is 2 to -x. -x means you flip it about the y-axis. Remember that? Okay, that's in the transformation part. So these two graphs are identical, except one is on the right side, the other one is on the left side. Okay, so but to get those two graphs, you just literally do the computation and try to plot those values. Okay, so like this, the base in the greater than 1, you have a list of 6 properties. For the base between 0 and 1, you also have a list of 6 properties parallelly. Let's see the parallel properties. The properties of the exponential function f(x) equal to a to x. Here, this a is between 0 and 1. Here we choose 1/2. You can choose 1 over 4, 1 over 3, whatever number, smaller number, or you can choose some irrational smaller number. It doesn't matter. You will always have a similar graph. Okay, similar graph. And for this one, for this case, we also have 6 properties. They're parallel. The domain is from -infinity to infinity. It's also defined over the whole number line. The range is from 0 to infinity. Because we only flip it about y-axis, we do not cross x-axis. Okay, so the first property is identical to the, you see, the first property is identical to the previous case. And second property, there is no x-intercept. And y-intercept is 1. This y-intercept is also 1 because a to 0 is always 1. Whenever you put x equal to 0, the value is always 1, right? Okay, so this is also the same thing. And 3, the x-axis is the horizontal asymptote as this. The last time it approaches negative infinity, this time as x approaches positive infinity. It's symmetric. It's symmetric. And 4, this moment the graph is a decreasing function. So fx equal to a to x is decreasing. Decreasing function is also 1 to 1. Okay, decreasing on the 1 to 1. 5 is actually the same thing. 1 x is equal to 0, you get a 1. 1 x is equal to 1, you get a. But this a is between 0 and 1, so it's less than 1. 1 x is negative 1, you get a 1 over a. Okay, so they are on the graph. And 6, the graph is smooth, continuous, with no corner and gaps. Okay, so they are almost identical. Only one is increasing, the other one is decreasing. Okay, so just compare them. Just compare them. One go up, the other one going down. Bigger base greater than 1, it goes up. Base less than 1, it goes down. Except that they are symmetric. One you reflect it to the other part, you will get the other one. So all the properties are similar. Okay. This list of the properties is on page 428. Okay. This is example. Graph fx equal to 2 to negative x minus 3. Okay, how do we graph it? So first, we sketch the graph y equal to 2 to x. This is 2 to negative x, be careful. 2 to x is like this. Okay, that's the first step. Second step, we just sketch the graph while I do not plot. Second step, you put a negative sign. This is fx. And if you want to study f negative x, you're going to reflect it about y-axis. So this is a 2 to negative x. Right? You have a negative x input, directly put a negative sign in front of x, then you get a reflection about y-axis. And then you minus 3. You subtract 3 from this 2 to negative x. You move it vertically down 3 units. So this is a 1. You move it 3 units down. It's a 0, negative 1, negative 2. So negative 1, negative 2. And so it's a... And 0 is moved to x-axis. It moved to the x equal to negative y equal to negative 3. So everything will be shifted down. This asymptote will be shifted down 3 units. Here it is y equal to 0. You shift it down 3 units, it's a y equal to -3. And the graph is also shifted down 3 units. This is -2. Here's a 1. 1 minus 3 is -2. Right? So that's the graph, the idea. And you can see that the whole graph is above the y equal to -3, so the fx is greater than -3, always. And the domain is the same thing. The range, this is about the range. -3 to infinity is a range. And the domain is negative infinity to positive infinity. Okay. Let's say exponential function. All the exponential functions satisfy the property we just discussed. But of course, we are not study all the rational functions. We are not study all the exponential functions. We study some special one. The special one comes from the special selection of the base. So how do we specially select a base? For arbitrary positive integer n, 1 plus 1 over n. When n becomes bigger and bigger, 1 plus 1 over n actually smaller and smaller. It's a decreasing function, right? Becomes smaller and smaller. When n is a 10, it's a 1.1. When n is a million, it's a 1.00001, right? So it's a decreasing function. And then we put the power, nth power. You multiply it a lot of times. This one, we can try the calculation. In the book, they gave you a list. When you choose n equal to 1, this value is equal to 2. Check that. When n is a 1, this is 1 plus 1 to first power. 1 over 1 is a 1. 1 plus 1 is 2, so it's equal to 2. And when n is equal to 2, it's 1 plus 1 half and squared. 1 plus 1 half squared is 1.5 squared. It's a 2.25. This value is an evaluation. And if you choose n equal to 5, 1 over 5 is 0.2. 1.2 to fifth power. It is equal to this quantity. And you can choose n is equal to 10. Still, you can compute it. It's about 2.59374246. And you can continually make this bigger. For example, in the textbook, they even gave some quantity. N is equal to, what is this? A billion. Yeah, 1, 0, 0, 0, 0, 0, 0. This is a million. 0, 0, 0. With non-zeros, this is a billion. When you get this a billion, this value, you don't have the concrete value, you just have estimation. It's about 2.718281827. So this sequence actually approach some number. That number is not rational, it's irrational number. So we define E as a limit when you choose this n bigger and bigger and bigger. So we use this symbol. N approaching infinity. What is the value of this sequence of numbers? This E is defined to be this number. And this E is approximately like this, 2.718281828 stuff. It's infinite. It's irrational. E is irrational. And E in this book, or in this current pre-calculus, we cannot discuss it in detail, but it is extremely useful in the calculus. In the pre-calculus, we couldn't see the why it is such important. Okay, but we do have a number. This number will be selected, and we like to use this one as a base. So we like to choose a equal to e in the fx cax. Okay, we like to use this number as a base, and this number, remember, this number is 2.7 stuff. E is greater than 1, so the graph of the exponential function is like this. It's an increasing function. Okay, it's an increasing function. Next, we just say there is a special choice. Other than 2, 3, 4, 5, 10 stuff, there is a special choice like this e. And the exponential function with this selection is called the natural exponential function. The natural exponential function. But so far, we don't see why it is natural. It's really not natural at all from this picture, but doesn't matter. Just keep this in mind. Okay, so after we have the exponential function, let's see how do we solve the exponential function. Exponential equation. Let's see how do we solve exponential equation. Exponential equation is solved as the following. If you have a to u equal to a to v, two exponential expressions are equal with the same base, then u must be equal to v. So this is the key. This is a key. Whenever you have e to u equal to a to u equal to a to v, then u is equal to v. Then let's try to solve some simple problems. So 3x plus 1 equal to 81. 3 to x plus 1 is equal to 81. 81. 81 is 9 times 9. 9 is 3 times 3. This 9 is also 3 times 3. So you have 1, 2, 3, 4. So it's 3 to 4. The reason we write 81 as a 3 to 4th power is that in this characterization, we need the same base. You cannot write 81 here. 81, that if you just write 81, there's no way to solve it. We must write this number as a exponential function with a base 3. You also cannot write it as 9 squared. 9 squared is useless here. So 3 to x plus 1 is equal to 3 to 4. So x plus 1 is equal to 4. The exponent is equal to the exponent. Then you get x is equal to 3. So this is a solution. Okay, this one is a solution. B. Remember, we need the same base. 4 to 2x minus 1 is equal to 8 to x plus 3. The previous example is simpler because 81 eventually can be written as a 3 to 4th power. But here, we know that 8 is not 4 squared. 8 is 2 times 4. It's twice of 4, but it's not the power of 4. So we cannot write 8 as any power of 4 and continue the computation. What we can do is the following. 4, we can write it as 2 squared. And 8, it is 2 cubed. So with these two realization, let's rewrite the left side. Left side, it becomes 2 squared and then 2 power 2x minus 1. Right side is 2 cubed and then 2 power x plus 3. By this, you have the same base. Okay, 2 squared and then to 2x minus 1 is 2 times 2x minus 1. You get the product of those two exponents. Right side is the same thing. 2 to 3 times x plus 3. Okay, now you have the same base. You have the same base. The exponents are the same. 2 times 2x minus 1 is equal to 3 times x plus 3. And then you solve it. So 4x minus 2 is 3x plus 9. So x is equal to 11. This is the solution. Okay? Next. E is just a number we defined. This letter is reserved for this purpose. Normally we use A, B, C, D. You can use them, but this letter E, you try to avoid it if you just want to use variable. E is a fixed letter for this number 2.7 stuff. Okay, don't use E to represent a variable. E is a number, like a pi. Okay, e to negative x squared is equal to e to x then squared times 1 over e cubed. Well, let's simplify it. The left-hand side is very simple. Let's copy the left-hand side. Right-hand side, e to x and then squared is e to 2x, right? 2 times x is 2x. 1 over e cubed is e to negative 3. 1 over the reciprocal means you have a negative power, negative exponent. And then e to 2x times e to negative 3 is e to 2x minus 3. This term plus negative 3 is a 2x minus 3. So e to negative x squared is equal to e to 2x minus 3. The exponents are equal. So this negative x squared is equal to 2x minus 3. Okay? So you move x squared to the right side, you get a 0 is equal to x squared plus 2x minus 3. Let's write it this way. We prefer to write 0 on the right side. Okay? And then you confect it, 1, 1, 3, negative 1. Okay? Put x here, put x here. So it's x plus 3, x minus 1 equal to 0. So you get x is equal to negative 3 or x is equal to positive 1. Okay, so these two numbers are the solution of the original equation. Okay, so far, when you solve the equation, exponential equation, you will always transform the left side and the right side as an exponential function with the same base. You have to do it with the same base. Different base, with a different base, you cannot do it. Okay? So this is a section 6.3. In the section 6.3, the solution to solve exponential equations, this part is more complex and tricky. So you have to be careful. And except that, you just memorize that when a is greater than 1, it's an increasing function. When a is between 0 and 1, it's a decreasing function. And that graph is important. And you have two graphs. Be careful, you have two graphs. One is increasing, the other one is decreasing. And also remember this number e. This number e is about 2.7, 2.71 stuff. It is irrational, and this letter is reserved for this purpose. Don't use it to represent other variables. Okay, do exercise, ask me questions. Thank you. We will continue in next video.